So in this video I'll be discussing about the hacked language specification. The hacked language instruction set contains only two types of instructions, that is the A instruction and the C instruction. The A instruction starts with an at symbol, and the value part is either a non-negative decimal constant or a symbol referring to such a constant. So this is an example of an A instruction where the value is a non-negative decimal constant. And this is an example of an A instruction where the value is a symbol referring to a non-negative decimal constant. So this variable name will refer to some non-negative decimal constant. So to encode our A instruction, we start with a 0 because the MSB of an A instruction is always 0. The opcode is always 0, and likewise the opcode of the C instruction is 1. So we start with a 0 and we concatenate the 15-bit binary representation of the value part, and thus our A instruction is obtained. So in the case of A instruction that refers to that has a symbol for the value part, there exists a map where the symbols are mapped to certain values. So we refer the map and it is replaced by a number, and that number is converted to the 15-bit binary representation, and we concatenate it to the 0, and thus we get the binary representation of the A instruction. So the next type of instruction is the C instruction. The symbolic representation of the C instruction goes like this. We have destination equals comp, that is compute, and then we have a jump. This is an example of a C instruction. So any instruction that does not start with an A instruction is a C instruction. So in the C instruction syntax, either this is optional, and C instruction can be any combination of these. So this is an example of a C instruction. We can see the destination part here, D for destination, D minus M for compute, JMP for jump. So what we basically do is we take each part of the C instruction, the destination part, the compute part, the jump part, and we convert these individual parts into their binary equivalent form, which you can see here, and it is represented like this. The binary syntax here, the first bit is 1 because it is a C instruction, the MSB is 1. The next two bits are ignored, so we just take it as 2 ones, and the next 7 bits that we see, A and C1 to C6, corresponds to the compare part of the C instruction. So these bits are used to represent the compare part of the C instruction. So to encode the compute part, what we have is a map, a predefined map called the compute map, as shown here. So what we do is we split the C instructions into 3 parts, and we look at the compute part. The compute part is D minus M, so we refer to the map and you search for D minus M. Here you can find D minus M. So it maps to this value. You can see C1 to C6 is mapped to this, and you can find the value of A from here. So we take the value and we concatenate this value to the previous ones. So that is how it's done. So next we have D1, D2, D3. These bits represent the destination part of the C instruction. So similarly, the destination part also has a map, as you can see here. So what we do is we look at the destination part and find out D in the destination map, and we find the corresponding binary values. and then similarly we just concatenate it to the previous string. Similarly, likewise you do the same for jump. Jump also has a map, a predefined map, which maps each type of jump to its corresponding binary values. So JMP is, you can see here, is 111. So you concatenate that to the previously concatenated string, and thus we obtain the machine code of the C instruction. Next, what we are going to talk about is the predefined symbols. They are simply simple symbols that are mapped to 15-bit binary representation of numbers that we see here. R0 to R15 are mapped to 0 to 15. Screen is mapped to this value. KBD is mapped to this value, and so on. Next, we have the label declaration. Labels are just something that we use to point to the instruction that comes after it. It doesn't translate to any kind of machine code. Next, we have the variable declaration. So suppose we want to represent a constant value with a variable name, with a name, and we use this. So now we'll discuss the assembler. This assembler is written in the Python language. So first you can see there are 4 dictionaries. These 4 dictionaries are our tables that I mentioned before. The first 3 dictionaries that you see, comp map, test map, and JMP map, correspond to the compute map, destination map, and jump map, which is used to encode our C instruction. Next, we have the symbol table. The symbol table, we map each symbol, a couple of symbols, to a certain value. That is what we can see here. For example, R is mapped to 1. R1 is mapped to 1. You can see R1 is mapped to 1. This is a 15-bit binary representation of the number. So this program mainly has 3 parts. First is a pre-process part, and then we have the first pass, and then we have the second pass. What we do mainly in the first part, in the pre-process function, is that we open a ASM file that is provided as our argument, and then we read it line by line, and we process it in such a way that all the white spaces and the comments are eliminated, and then we store each instruction line by line into a list. So the program is in order inside the list. That's the list BGM. So once that is done, we move on to the first pass. In the first pass, what we do is we take the list that we created before, the PGM, which contains our program, and then we read it line by line, and we check if the line matches this pattern. If it matches this pattern, what we do is we extract the middle part from here, and we store it in the dictionary in the symbol table, and then we map it to the address of the next instruction, that too in the binary 15-bit binary representation. And offset is used to find the address of the next instruction. And each line which is not a label is appended into this another list called PGMV2. That is what we see here. So PGMV2 now contains the assembly program without any labels. So next we have our second pass. This is where the translation takes place. Here you can see I have opened a file in write mode, a file called file.hack. This is where our encoded instructions are stored line by line. So we start reading the list that we created earlier, PGMV2. So we start executing it we start reading it line by line. So if the instruction start with an @ symbol, then we know that it is an A instruction. So now we check the value part of the instruction. The value part is a digit. We simply convert it to the 15-bit binary form, and then we append it to 0, and thus we get our encoded A instruction. Next, if it is not a digit and if it is symbol, we search the symbol table for the value of the variable. If it is not found, what we do is we insert the variable name and we give it a value which is already initialized here. We start with n equal to 16 so that variables can be given values. So we give the value n and encode it in 15-bit binary, and we store it in symbol table, corresponding symbol position of the instruction. Then we increment our n. And then finally we append the value to 0, and thus we get our instruction. So the next part is the C instruction part. So basically what we do here is we take the instruction and we split it into 3 groups. We can see that here using the RE module. So these 3 groups corresponds to the 3 groups in the C instruction: destination, compute, and jump. What we do is we simply check the symbol table and we append the corresponding binary values into the string, and thus we get our encoded C instruction. And we write the instruction that we obtain into the file, the hack file. So this is the working of our assembler. Now I'll demonstrate the program. Okay, this is an assembly program. So this is the program that we are going to encode. So we encode it. It takes our hack assembler program takes one argument, that is this program, and once you execute it, a file will be created in the current directory called file.hack. So that file will contain our encoded program. So you can see that here. This is the encoded machine instruction.